Water management is closely tied to the management of your solutes, especially sodium. Your body doesn't control water directly compared to how it really uses solute concentrations to control water. When thinking of water management in nephron, you first have to recognize that the PCT and the DCT are tasked with reabsorbing a lot of stuff, right? A lot of ions, cations, molecules, right? More so for the DCT, especially if it's under the control of certain hormones. So as these solutes get reabsorbed, they give this great opportunity for water to flow with it by passive transport. The medulla of the pyramids increase in osmolarity toward the renal basin. So the loops are always subjected to a tonicity that like pulls water from the descending loop arm. Looking at this diagram here, you can see that water is never, ever, with one more, ever, it's never transported actively. That is not something that these cells or the nephron is set up to do. They don't have active transporters for water, but they do have active transporters for solutes. And by making areas of high tonicity, we can control the direction of the flow of water. The nephron employs two different methods of controlling water loss or reabsorbing water. Those are kind of opposites there. Obligatory water reabsorption is the movement of water from the filtrate to the peritubular capillary or the vasa recta, and that movement that happens in the proximal convoluted tubule, or the descending nephron loop. If the loop dips deeper into the medulla, which loops of those juxtamedullary nephrons do, then that descending arm of the loop will be able to reabsorb more water. Cortical nephrons, in contrast, they don't dip as deeply into the medulla as juxtamedullary nephrons, and therefore cortical nephrons have a lower capacity of obligatory water reabsorption than do juxtamedullary nephrons. We know that there's no capacity for the ascending arm of the nephron loop to move water in either direction. It's all that descending loop. The DCT and the collecting duct, yes, they are capable of reabsorbing water, but they can only do that under the influence of hormones. And that hormonal water reabsorption is what is known as facultative water reabsorption. So obligatory water reabsorption happens all the time, and facultative water reabsorption happens only under the influence of these hormones. In fact, your cortical nephrons in total don't have the ability to keep you alive on land. You always have to employ these juxtamedullary nephrons. Let's do an example of how hormones, one that we know of, influences water reabsorption. So for example, low blood pressure can trigger the release of the antidiuretic hormone, or ADH, from the posterior pituitary gland. It's going to float around in systemic circulation until it comes to the kidney, and then it's going to attach to some of those simple cuboidal cells of the DCT and the collecting duct. Upon attachment, it's going to facilitate the making of a protein called aquaporins that will then be inserted into the cell membrane of these cells, and it will give a channel and allow water to be reabsorbed. Without these aquaporins, water loses the opportunity to follow all of the solutes that are being reabsorbed in the DCT. That's a great opportunity for passive movement of water. I don't want to miss that. When ADH is turned on, you have an increased capacity to reabsorb water or an increased capacity to conserve water. This would reduce your osmolarity by watering you down, but it would increase the osmolarity of your urine. And therefore, this would, as I said, increase your water content. But it would it would decrease the water content of your urine, giving you a smaller volume and also giving you a more concentrated urine. Obligatory water reabsorption is never enough to satisfy the needs of an enormous organism like a human on land. Kidneys in general, whether human or otherwise, kidneys are excellent adaptations to conserving water for a life on land. However, the mere presence of those juxtamedullary nephrons in mammals is it's kind of a testament to how obligatory water reabsorption it would just never be enough without these nephrons. Recall that the medullary pyramids all come to a point at that renal papilla that weeps urine into the minor calyces. As you get closer to the point of that pyramid, the interstitial fluids of the pyramid become more and more concentrated with solutes. This creates a situation in which there is an incredibly high tonicity outside of the nephron. This high tonicity, it sucks water from the filtrate, moving through the descending arm of the nephron loop. As previously mentioned, if that loop is longer, as it is in a juxtamedullary nephron, there will be more obligatory water reabsorption. Another key player in obligatory water reabsorption is it's not just the length of that nephron loop, but also the fact that juxtamedullary nephrons are surrounded by a vasa recta capillary bed. Vasa recta capillary beds are incredibly organized into a very distinct arterial side of the bed that hugs the ascending nephron loop arm, and then a venule side of the bed that hugs the descending nephron loop arm. You might think that what I just said was a mistake because there's a venule side of the bed and you're like, wait, that's got to be closer to the end of the nephron. No, the direction of flow of the filtrate in the descending nephron loop has to be completely opposite to the flow of the blood in the capillary with which it exchanges. The same applies for the nephron loop on the ascending side. The capillary bed with which it is associated has blood flowing in the opposite direction as the filtrate in the nephron. This is what is called a countercurrent multiplier, or a countercurrent multiplier mechanism. The sheer fact that the fluids are flowing in the opposite directions increases the exchange rate between them. This is the same concept that's used in dialysis, where a patient's blood is circulated countercurrent to some diazolate. This countercurrent mechanism, again, it allows the greatest exchange of both solute and water. Countercurrent mechanisms can be for more than just solids and liquids. They can also be for temperature and even for pressure. Obligatory and facultative water management affects the properties of urine having to do with the proportional amounts of water and solutes. The easiest way to determine solute to solvent proportion is to look at the color. Darker color means that you have a lot more solutes, whereas a lighter color means that your urine is much more watered down. Specific gravity compares the weight of your urine to 1 unit of water. So if your specific gravity is above 1 or below 1, therefore, if your urine is heavily laden with solutes, your specific gravity is going to increase. I think of specific gravity as the weight, but you can't, that's not entirely accurate. A high specific gravity indicates a very concentrated urine and could possibly be from somebody who is under the influence of ADH. There is one more thing that we measure with urine that also indicates the proportion of solutes to solvents. This measurement is osmolarity. I find that students, when considering urine and osmolarity and pH, students get very mixed up as to what's in the blood and what's in the urine, which should be opposites usually. For example, urine that has a high osmolarity is very concentrated. So highly concentrated urine would be from someone who's under the influence of ADH and someone who is desperately trying to conserve water. Try to think of urine as a solution to problems present in the blood. And what I'm going to put out here, this is kind of a poor example, but if you have high blood volume, you might be getting rid of a lot of water in your urine to try to fix that, right? In a way, the urine is helping you solve an osmolarity problem in your blood by decreasing or increasing the osmolarity of your urine. Let's use another example that's probably a little bit more common. Let's say, for example, that you are horrendously dehydrated because you drink way too much coffee. The osmolarity of your blood is high, and your body could be trying to get rid of solutes in order to decrease your osmolarity or in order to decrease the solute load in your blood. I mean, yes, you could possibly drink water, but thirst is it's a little bit more complicated mechanism than you might think. And right now, let's just think about outputs and not mess up the model with inputs.